Hello, Year 10s. Today we want to talk about forces and vectors. So I'm going to need you to make sure your books are open and you're following with me. Today we're going to be looking at forces and vectors. So previously in our classes we have been looking at how to describe motion, and we've been doing that in a few different ways. Don't draw this, but we've been looking at, say, displacement time graphs, something look like this. We've been looking at velocity time graphs. You know, and we've been computing the gradients of these objects, finding the area underneath them, which tell us certain properties. But today I want to talk about a different entity. I want to talk about forces. Now, let's just dive into what they are, and hopefully the connection with motion will be very, very clear. So, in simple terms, a force is a push, pull, or twist. Okay, is a push, pull, or twist. It causes things to accelerate in general. That's not always true, but we'll look at those cases later. It causes things to accelerate. So before we talk about how we calculate the overall force on an object or what it does to the motion of an object, let's see if we can identify a few different types of forces here. So let's say, for example, I'm going to attempt to draw here, and this is going to go poorly. Let's say we have a car. We have a car here. My artistic skills have not changed since grade 3, but whatever. Okay, we have a car here. Here's you in the car. Alright, so what forces would be acting on this car? I want you to think about that for a second. What forces would be acting on the car? Hopefully you would agree that there is some kind of driving force. Some driving force. I'm representing that by an arrow. We'll talk about these arrows in a moment. Hopefully you also agree it's affected by gravity. Gravity, force due to gravity. In addition, when a car is moving, it might be pushed back due to air resistance. So you might have some, air resistance here. And if you're unsure what that means, air resistance, I would highly recommend you at this very moment, air resistance, to take your hand, put it outstretched, and swish it through the air. And you should hopefully feel yourself moving through the air. What you're feeling there is air resistance, the air pushing back onto your hand. In addition, if the car is on a road, oops, oh, what did I just do there? No, I don't want pencil. You can tell this is live, no outtakes, so no double takes. Here we go. So you can hopefully you also agree that the ground is also pushing up. We'll call it like a support force. Right? The ground is pushing back up on the car. Right? In the same way, if you push down on your table kind of pushes back in a way. So these are all different types of forces. The driving force is kind of pushing the car forward. Gravity is pulling the car down towards the center of the earth. The support force due to the ground is pushing back up. The air resistance is pushing to the left. There are just some examples, but you can get other ones too. Let me attempt to scroll. Here we go. Let's see this one. Let me attempt to draw this. I recommend you do the same. No, not pencil. Let's go black, and thank you. I'm just going to delete that. Let's go. Okay, so here's a helicopter. Not a very good helicopter, but a helicopter nonetheless. Okay, so what forces act on this helicopter? Let's say it's hovering in the air. The ground is down here. What forces act on it? Well, hopefully you agree. Gravity. It's on this. And it's a force due to gravity. And notice how I'm labeling it. Yeah, force, gravity. Force due to gravity. But in addition, there's not just that force, right? That force would be pulling it towards the ground, but clearly if a helicopter is hovering, it's not going towards the ground. So maybe there's something else going the opposite direction. Indeed, there is. There is a force due to lift. Yeah, due to the rotors here. So this is another two examples of different types of forces. You can get many other different types of forces. You can get like pulling on a rope. You can get force of a kick. You can get force of buoyancy. Many other different types. These are all different types of forces here. Okay? I guess the most common ones that you'll experience in your everyday kind of world is force due to gravity. Probably a support force. You're feeling one right now as you're sitting in your seat. Hopefully you're sitting down. You might feel a driving force if you're going towards school, or maybe a push force on the ground if you're walking to school. And air resistance, of course, you feel all the time. Air is just impacting on you and slowing you down. Okay, now you'll notice I used arrows to represent forces. This shouldn't be uncommon. You actually did this back in year 7. Let's talk about these arrows in a bit more detail. So these arrows represent vectors. Right? They represent things with direction. So consider these two now. So here's a little subheading, vectors. Okay. Let's consider these two arrows. This one, we'll call that arrow A, and we'll call this one arrow B. Arrow B. All right. So these two arrows could represent any vector. Let's imagine that they represent forces. What do you think these two forces? Well, let me start that sentence again. What do you think is similar about the arrow representing force A and the arrow representing force B? I'll invite you to think about it. The answer here is that one, they're both pointing in the same direction, right? They're both pointing to the right. So if this was an arrow for force A, this was an arrow for force B, who knows what those forces are? They could be, I don't know, force of thrust or drive or push or pull, doesn't really matter. They're both pointing in the same direction. Hopefully that's obvious. Both arrows are pointing to the right. But in addition, you'll notice that the arrows are roughly the same length. Roughly the same length. What that means is that the forces are actually the same size. Okay, so the length of the arrow represents the size of the force, whilst the direction of the arrow represents the direction of the force. Let's go ahead and write that down. So size equals to size of the arrow equals to the size of the force, and direction. Well, this seems very obvious, but I guess whatever. Direction of force. Okay, so for example, here's another example. Let's consider this. Let's consider this. Please write with me. So this is F A again, and this is F. We'll call it FC, force C. What's the difference between these two? And what's similar about these two? Again, pause for a second, think about it. Hopefully you would agree they are the same size of force, but they're pointing in opposite directions. Now, when I say size of force, I mean they literally measured to be different magnitudes. If you recall, maybe we actually should put it back up here. Forces are measured in units called newtons. Forces, the unit of force, is the newton. Given symbol N is the newton. So what these arrows mean down here is that, say for example, F of A is 10 newtons. FC, if it's the same length arrow, is also going to be 10 newtons, but it just means the force is pushing to the left. Okay, is pushing to the left. You can get forces in not just left-right directions. You can get forces in up-down directions. That's fine too. I'm just looking off my notes here. Anything else I need to talk about? No. Okay. Alright, so the next question is, what happens when you combine these arrows together, these forces together? What's the overall effect on an object? What's the overall effect on an object? So to demonstrate that, I'm going to use this little simulator here. So let's just chuck some of these on. So let's put this person here on this rope. You can see they pull to the right with 150 newtons. And if we actually let this simulation run, you'll notice that the cart goes to the right. Not just goes to the right, let me actually return it back to the original position, but the speed increases. So this object is accelerating. That's what the force is doing, it's accelerating. If we added more, let's add all people. Not sure why they're different size, but whatever. You'll notice that the more force there is, the quicker it accelerates. Right? Hopefully that makes intuitive sense. Now, what do you think what would happen if, say, I took this person and I put the same person on the other side. I have two forces here. I have a force to the right of 150 newtons, a force to the left of 150 newtons. The arrows are the same size, but they're in opposite directions. What do you think is going to happen? Well, hopefully you agree that the object is not going to go anywhere. Okay, it's actually not going to accelerate. It's not going to accelerate. Let's actually calculate the overall force here. The overall force, what do you reckon it would be? 150 to the right and 150 to the left. Well, the sum of the forces would be zero. Mathematically, we can represent it. We can represent it like this. I'm hoping I'm still recording my screen. Here we go. We can represent it like this. So let's say you had a cart here, and it's getting pulled to the right with 150 newtons and pulled to the left with 150 newtons. What is the overall force? Sometimes you write it like this. Right, this is capital sigma. This means sum. What is the overall force? Well, the way I typically calculate it is I'll say, let's say anything to the right is positive, anything to the left is negative. Then my forces is a positive 150 due to that, minus 150 due to that. Right? Or if you want to be more explicit, plus negative 150, because we're always adding the forces, but this one's in the opposite direction. This, of course, equals to 0. So it makes sense. Good. Let's do a different example. What would happen if instead I put this person on? And they can only pull with 50 newtons to the left. I guess my first question is, what do you think is going to happen to the cart? Well, hopefully you would agree it would still go to the right. It's actually accelerating to the right. It's accelerating a bit slowly though, and you'll notice if I made this more apparent, if I made the left force 100 newtons and let it run, we still have an overall force to the right, but it's accelerating even slower still. So why does this happen? Well, it's because the sum of the forces are different. The overall force is different now when I have one person or no people or two people. Let's actually calculate what the overall force on this cart is. So let me click sum of forces. There you go. The sum of the forces is 50 newtons to the right. Hopefully that makes sense. You have 150 to the right and 100 to the left. So the overall force, the leftover force, is 50 newtons to the right. Right? That's what happens when you add up these two vectors. Mathematically, we can represent it like this. You can represent it like this. Let me make sure I have a new page. Can I do that when I haven't scrolled down? No, I'll just, there we go. Let's have a look at what's happening here. So if I now have 100 newtons to the left, yep, let's see how the situation changes. The sum of my forces is, again, positive 150 plus negative 100 equals to positive 50. So there you go. We have 50 newtons left over, and because it's a positive value, it is to the right. Right, and that's exactly what we see in the simulation. Okay. All right, now here's a fun question, a fun little thought experiment. Let's say we had this person to the right. Okay. Actually, yeah, to the right. Let's let it go. It's accelerating to the right. Wonderful. Let's say I chuck on this person to the left. What is the overall force? Hopefully you agree it's 150 minus 150, 0. What's going to happen to the speed? I'm hoping some of you might have thought it stays at 0. Well, you're wrong. The speed actually just maintains. It keeps on going to the right, even though the sum of forces is 0. Now, don't let that disturb you in any way. Remember what a force is. A force causes acceleration. It doesn't give you a value of the speed. It just tells you whether you're going to speed up or slow down. So initially, when we had this one person, this system is going to speed up. And that is true. Look, it speeds up. When I balance out the forces, it stops speeding up. It means it maintains whatever speed it had before. So it continues at the same speed. And there you have it. That is an introduction to forces. What I'd like for you to do now is to work through page, let's see. I want you to work through page 19 to 22. 19 to 22 of your booklet, please. In 19 to 22. Work through that, help each other out, and then in period 2, you'll get the chance to do a bit of a practice test, and then in tomorrow's class, you can you'll have some time with me to do some specific revision. So if you have any questions, please make sure you do keep them for tomorrow. Wonderful. Thank you so much, team. Happy studying.